we did an aldol reaction, and we did an aldol reaction with two of the same aldehydes. Oh, okay. Aldol, because aldehyde, we don't use compounds for them because they've got two sides. All right, aldol. So we use two of the same to do an aldol reaction, and then we did the dehydration of an aldol, and that basically, it doesn't have to happen. It's not a step that necessarily has to happen after an aldol reaction, but generally it is done. Like you have to use acid or base to promote the aldol reaction to happen anyway, right? To promote the dehydration, you have to use acid or base to catalyze it and heat it. So I'm sure that there are some that if you don't heat it, you just end up with some of it dehydrating anyway. I'm not entirely sure, but I bet that that's the case, just for certain weird ones. But yeah, I think most of the time you're gonna go ahead and an aldol just, as default, it just pretty much has a dehydration step after it. So today we're gonna do a crossed aldol reaction. This time we've got one molecule being the enolate anion and a different one being the carboxyl group. So basically, it is successful when one of the two reactants doesn't have any alpha hydrogens and cannot form an enolate anion at all. Otherwise, you get a hot mess, right? Because you're gonna get, if you have two just normal, let's go with aldehydes or symmetrical ketones. Let's just do that for now, for simplicity's sake. If you just do two normal ones and try to do a crossed aldol, you're gonna get an aldol of two of these, an aldol of two of the other one, aldols of this one being the enol and this one being the nuclear electrophile, and then aldols of this being the enol and this being the electrophile. So four very, very similar molecular weight things with very, very similar functional groups and therefore polarity, and that column is going to make you tear your hair out and maybe cry depending on who you are. You know, maybe. Lab does that, grad school does that. So, we only do crossed aldol when one of them just cannot be an aldol, an enolate at all, just can't do it. In this case, we've got a symmetrical ketone, and is that formaldehyde? Oh, yeah, here we go, formaldehyde. So just, you know, CO, but hydrogen on either side. We also like to do, oh yeah, there's benzaldehyde. When I showed you yesterday, there's a couple more that are commonly used as a reagent for this, since they don't have any alpha hydrogens. So it also helps if the same reactant, so the one that doesn't have any alpha hydrogens, it helps if this guy has a more reactive carbonyl group. So, because you still could get some of this becoming an enol and attacking itself, right? But if you get one of these that is a much more reactive carbonyl group, you can kind of get, for example, now aldehyde, then you can promote that to happen better. So, more reactive carbonyl group, aldehydes are more reactive because, do we remember that? Aldehydes, more reactive carbonyl groups. The carbon on an aldehyde is more electrophilic than the carbon on a ketone, right? Because there's less electron density around that carbon, because carbons and hydrogens, they're not exactly like electron withdrawing. They don't really care that much. So they're like, if anything, electron donating-ish, but like only a little. So having a hydrogen there just, I mean, you just don't have an octet, right? Versus a whole carbon that has an octet that's sharing. So, yeah. All right, so we do not have a mechanism for this guy. The mechanism's the same as the other one, except now you have two whole different things to keep track of. In which case, sometimes it's fun to draw both starting materials in just different colors entirely, instead of just marking the nucleophile and electrophile in different colors, but also still mark your nucleophile and electrophile. Always do that. Make sure your bond ends up between those. Nitro groups can be introduced into aliphatic compounds by way of an aldol reaction, because you can do the anion of a nitroalkane, this guy, that's a nitro group. There we go. That's the nitro group, and if this kind of looks like a carbonyl, then like a carboxylic acid, deprotonated carboxylic acid, yeah, it kind of does, right? So these hydrogens are actually kind of acidic. They're pK 10.2. That's pretty acidic. Like, I mean, in the world of, well, okay, water's 15.7, so in order to have water that is almost entirely, half of it exists as water and half of it exists as hydroxide, you have to have a pH as high as 15.7, right? Which kind of makes sense. That's, I mean, we pretty much in Gen Chem use pH on a scale of like 0 to 14, 15, because, well, we're using stuff in water, and 7 is the middle because that's neutral. But for these guys, 10.2, that's like within our Gen Chem range of pChems, of pHs, right? So that's like, it's not like 50 or anything wild. You have a fairly basic solution, pH 10, you would have an equal amount of nitromethane and its anion, which is resonance stabilized, right? So you can do the same thing that we did before, except this guy is going to be our enolate, sort of. I mean, it's not an enol, but like this one acts like our enol. It's our anion, our nucleophile, and you can react that with a carbonyl to do a crossed aldol, right? And you're going to get an NO2 group on there. And then you can use hydrogen gas and a transition metal catalyst to turn that into NH2. And that's really useful because, well, that gives you beta amino alcohols, which is a thing that people use, I guess. And also, this is just, you're taking a carbonyl and you're able to turn this into alcohol and nitro, and then you can turn that further into this. So you've got a lot of options with what you're going to do with things, right? Chapter 23 is amines, right? Yeah, chapter 23 is amines. Man, Smith recovers that in a day. I really need to figure out what he finds important in that chapter, because, like, it's not a short chapter. He just, I guess, doesn't matter that much. Did you guys cover nitro groups at all? Okay, cool. So they exist, NO2. I'm sure you guys have seen NO2 as like a substituent, but this is what it looks like. So there's not really a resonance structure of this that isn't charge separated. I mean, there's an extra charge separated where we've got, well, okay, there's an extra charge separated for this one, where we would have, let's see, N, O, there. And we can resonate like this. We're going to resonate in 3 steps, because why not? Oh, that's not a Z. You can kind of do that, and then that, and then from here to there, that's that. So that's what a nitro group looks like. And there's pretty much always some charges going on in there, but net, it's neutral, right? Because negative, positive, negative, positive, negative, 2 positives, and not a full octet, because usually when we've got a nitrogen with 3 bonds, it's not charged, right? Usually when we've got nitrogen with 3 bonds, it has a lone pair, because nitrogen likes to have its own lone pair. So, like, this is technically a resonance structure in, like, that's technically a resonance structure the way that this is technically a resonance structure. Except this is more dramatic, right? So this is like, all right, carbon doesn't have a full octet, and it normally has 4, or it brings 4 valence electrons to the table. So right now it's got, well, half of each bond, so 3. This, way worse, because nitrogen brings 5 electrons to the table, so it's used to sharing 3 bonds and having its own separate lone pair, and we just sort of took its lone pair away from it. So this is like, sort of, you know. Let's see. So we can do crossed aldol reactions. It doesn't have to be the same aldehyde. And we can introduce nitro groups and pretend that those guys are kind of like an enol and just use it in the same way. We can have intramolecular aldol reactions. These guys, the examples of these get a little bit wild because, like, I have some, once they start drawing rings, like, either there's already a ring and then there's a substituent, like a chain, and then they make that ring, so then you've got this ring that's like, it's like loop, 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 like a ring and then a bridge on it, but really it's like a sphere where you just have 3 sphere holding structure, you know? It's weird. And there are, they try to test you on some of those. Some of them with like really just wild structures. I always think they're fun to look at and maybe assign for like homework, but exam situations are stressful. So I'm not gonna make 3D drawing and drawing rings of like, I don't know, some of those are rings of like 13 or like a 7-membered ring with like a 6-membered like jut out or something. I don't want to put those on your exams, but they are kind of fun. Not that I won't necessarily put some sort of aldol, intramolecular aldol reaction on there. So, intramolecular aldol reaction, if you want, let's see, this, conveniently enough, 2,7-octane dione is symmetrical. So we don't have to figure out a bunch of all the possible products and then go and switch it and do it again, right? But even so, even though it's symmetrical, there are two possibilities. We can deprotonate, this side. We can deprotonate at alpha 1 or alpha 3. And in this case, they used KOH, so they did a base catalyzed aldol reaction. And if you deprotonate alpha 3, then you end up attacking right there, and you get a nice 5-membered ring. And then you dehydrate, and you get a nice 5-membered ring with a double bond. And if you were to deprotonate alpha 1, then you would take from here and attack. You would get a 7-membered ring, right? 1, 2, 3, 4, 5, 6, 7, yeah, which is like a nightmare and a half, like a nightmare and 3/4 to draw. I do not like them. They always look stupid when I try to draw them by hand. It's dumb. Thankfully, nature doesn't like them either. Nature is all about the 5- and 6-membered rings, right? So not only could we say, well, the enol with a double bond here is going to be more stable than the enol with a double bond here, right? That's true. Or just the charge separating structure. A negative charge on this carbon is more stable than a negative charge over here, right? Just because it's more substituted, so it's slightly more stable. So that's true, but not true enough that we can usually just do a bunch of aldol reactions and hope that we don't get a huge mess because one of them is slightly more favored. But nature loves 5- and 6-membered rings. So partly because of this, but mostly because nature's just all about the 5- and 6-membered rings, and if at all possible, it will favor that or just entirely not form the other one. We only get this one from this guy. Yeah. When we do intramolecular aldol reactions, I mean, there's basically going to be like, you can always have, 2 options unless this is a dialdehyde. Dialdehyde. In which case there's, well, one thing you can do. But always look for the 5- and 6-membered rings because that's when you're going to actually have product favored, and that's actually when you're going to have one of your 2 products favored. And this guy, we could deprotonate here or here. And again, alpha 3 is more stable, right? To have the negative charge on it or to have the double bond for the enol over here, that's going to be slightly more stable than this. But if we attack from here to there, right, we're not attaching this carbon to this oxygen. Actually, let me do arrows because I think that will be easier than just pointing a lot. I'm going to leave this back here so we can see that. Okay. Masterful hexagons. So good at those. Okay. So, this is going to be our electrophile, right? And our nucleophile is either going to be alpha carbon 1 or alpha carbon 3. Remember, we're not trying to make this into a ring, right? You don't make a bond between your nucleophile and this oxygen. we have a nucleophilic attack. These guys are our nucleophiles, and we attack this carbon. Well, if we take this guy, and we end up attacking there, I can draw an attack arrow, but also instead I can draw just sort of a line to pretend that we've made a bond there. If we try to make that a bond, how many members are in that ring?
4.
4? What are your bond angles gonna be?
90 degrees.
Yeah, like 90 degrees, because how else do you make a square? And I don't even think you can really, I think no matter how much you twist it, if you've got a 4-membered ring, I don't think there's any way to make that without 90-degree angles, even if you have like, I'm picturing it in 3D space. I don't think there's any way to like, even make those slightly different. Like you have 90-degree bond angles. Nature hates this. So even though this enol, or the enol on this side would be slightly more stable, the negative charge on alpha carbon 3 would be more stable, would be favored. That super doesn't happen, right? So what about this one? 1, 2, 3, 4, 5, 6. Ooh, that makes us a 6-membered ring. That's like nature's favorite thing. So that's how we know which one is going to happen. And that's why these intramolecular aldol reactions are, basically like, it's okay that we always have 2 sides where we can form our nucleophile. In this case, we don't like start just always using